Now let's discuss the time shifting property. If xt and x omega are a pair of Fourier transform, then xt minus t0 and x omega exponential negative j omega t0 are a pair of Fourier transform. This result shows that delaying a signal by t0 seconds does not change its amplitude spectrum. The phase spectrum, however, is changed by negative omega t0. This property physically explains linear phase shift in the spectrum due to time delay in a signal. So let's consider a signal xt. We know a signal xt can be expressed by its Fourier components, so which are sinusoids of certain amplitude and phases. The delays of the signal xt minus t0 delays are the same sinusoidal components by t0. The amplitude of the components remain unchanged. However, the time delay t0 in each sinusoid does change the phase of each component. Therefore, a time delay t0 in sinusoid of frequency omega manifests as a phase delay omega t0. This is a linear function of omega, meaning that high frequency components must undergo proportionately higher phase shifts to achieve the same time delay. This effect is illustrated in this figure with two sinusoids. The frequency of the lower sinusoid being twice of that the upper. The same time delay t0 amounts to a phase shift of 2 pi in the upper sinusoid and a phase of shift pi in the lower sinusoid. This verifies the fact that to achieve the same time delay, higher frequency sinusoids must undergo proportionately higher phase shifts. Now let's look at one example. Use the time shifting property to find the Fourier transform of exponential negative a absolute value t minus t0. Earlier, we found the Fourier transform of this function xt. We know its Fourier transform is x omega 2a square plus omega square. Then to apply the time shifting property, when there's a time shift t0, it will cause a frequency shift. So therefore, the Fourier transform of the signal will be 2a square plus omega square exponential, so negative j omega t0. The spectrum of this function is the same of that of the exponential negative a absolute value of t, except for an ideal phase shift of negative omega t0. Observe that the time delay t0 causes a linear phase spectrum, negative omega t0. This example clearly demonstrates the effect of time shift. Let's discuss the frequency shifting property. If xt and x omega are a pair of Fourier transform, then the Fourier transform of xt exponential j omega 0 t is x omega minus omega 0. If we change omega 0 to negative omega 0, we have this result. The Fourier transform of xt exponential negative j omega 0 t is x omega plus omega 0 t. Because exponential j omega 0 t is a complex function that cannot be generated, frequency shifting in practice is achieved by multiplying the xt by sinusoid. Observe that the xt cosine omega 0 t is half xt exponential j omega 0 t plus xt exponential negative j omega 0 t. Then based on the results shown here, we know the Fourier transform of xt cosine omega 0 t will be half x omega minus omega 0 plus x omega plus omega 0. According to this property, the multiplication of a signal by a factor of exponential j omega 0 t shifts the spectrum of that signal by omega the same with omega 0. Note the duality between the time shifting and the frequency shifting properties. Multiplying of a sinusoid cosine omega 0 t by xt amounts to modulating the sinusoid's amplitude. This type of modulation is known as amplitude modulation. The sinusoid cosine omega 0 t is called the carrier. The signal xt is the modulating signal. The signal xt cosine omega 0 t is a modulated signal. So when you look at this figure, the xt cosine omega 0 t touches xt when the sinusoid cosine omega 0 t is at its positive peaks, and touches negative xt when cosine omega 0 t is at its negative peaks. This means that the xt and negative xt act as envelopes for the signal xt times cosine omega 0 t. The signal negative xt is a mirror image of xt along the horizontal axis. The two figures at the right-hand side show the signals of xt xt cosine omega 0 t and their spectrum. This is for you to practice the amplitude modulate signal, sketch the signal, exponential negative absolute value of t times cosine 10t, and find the Fourier transform of the signal and sketch its spectrum. The next drill is to show that xt cosine omega 0 t plus phi is a Fourier transform is half x omega minus omega 0 exponential j theta plus x omega plus omega 0 times exponential negative j theta. Let's discuss the applications of modulation. Modulation is used to shift signal spectrum. There are some situations that call for spectral shifting. I will give you two examples. The first example is related to radio stations. If several signals are occupying the same frequency band are transmitted simultaneously over the same transmission medium, they will all interfere. It will be impossible to separate them at the receiver. For example, if all radio stations decide to broadcast audio signals simultaneously, a receiver will not be able to separate them. This problem is solved by using modulation. Thereby, each radio station is assigned a distinct carrier frequency. Each station transmits a modulated signal. This procedure shifts the signal spectrum to its allocated band, which is not occupied by any other station. A radio receiver can pick up any station by tuning to the band of the desired station. The receiver must now demodulate the received signal. Demodulation, therefore, consists of another spectral shift required to restore the signal to its original band. Note that both modulation and demodulation implement spectral shifting. Consequently, demodulation operation is similar to modulation. Another application I'd like to discuss is the size of antenna. The use of amplitude modulation to change the frequency content of a message from its baseband frequencies to higher frequencies makes the transmission of the message over the airwaves possible. So let me explain why it's necessary to use AM to transmit a music or speech signal. Typically, music signals are audible up to the frequency about 22K hertz. So here, so 22K hertz. Well, speech signals typically have the frequencies from about 100 hertz to about 5K hertz. So therefore, music and speech signals are relatively low frequency signals. When radiating a signal with an antenna, the length of antenna is a quarter of the signal wavelength. So the size of the antenna will be a quarter of this wavelength. So lambda is a wavelength. So lambda is equal to 3 times 10 power of 8 over F. The unit is meter. Then F is the frequency in hertz. 3 times 10 power of 8 is the speed of the light. So therefore, if we assume that frequencies up to F, like say, so F is 30 K hertz. Okay, if F is 30 K hertz, then the wavelength lambda is about 10 kilometers. 10 kilometers is about a mile and a half long antenna. In practically, large antennas would be required for station, but this is definitely not possible. Here, shifting the spectra to a high frequency by modulation solves the problem. Therefore, for music or speech signal to be transmitted with a reasonable size antenna, requires one to increase the frequency present in the signal. Amplitude modulation provides an efficient way to shift acoustic or speech signals to a desired frequency. The time convolution property and its dual, the frequency convolution property states that if x1 and x1 omega are a pair of Fourier transform, and x2 t and x2 omega are another Fourier transformation pairs, then the time convolution property states that the convolution of x1 and x2 is Fourier transform is x1 times x2. In time domain, it is the convolution. In frequency domain, it's just the multiplication. The frequency convolution property states like this. In the time domain, signal x1 times x2 is Fourier transform. In the frequency domain is 1 over 2 pi x1 and x2 omega convolution. I will give you 2 questions to practice. Use the time convolution property to show that the convolution of xt and delta t is xt. The convolution of exponential negative at times the unit step signal and exponential negative bt times unit step signal, the convolution of the two is 1 over BA exponential negative AT minus exponential negative BT times the unit step signal. The last property we would like to discuss is the time differentiation and time integration. If xt and x omega are a pair of Fourier transform, then the Fourier transform of time differentiation dxt over dt is j omega x omega. And the time integration of x tau from negative infinity to t is Fourier transform is x omega over j omega plus pi x0 delta omega.